Today, we're going to be geological detectives. We're going to learn how to read the incredible story our planet has written for us, a story that isn't found in books, but in the actual rock right under our feet.
And I just love how our source material frames this. Earth's history really is an adventure, filled with these epic forces like earthquakes and volcanoes. But it's also a deep mystery because we can't just slice the planet open to see what's inside. So that's the big question, right? How do we solve this thing? How do scientists piece together a history that stretches back billions of years, using just the clues we can find on a world we can't fully explore? Well, the answer starts deep, deep down.
Our first big hurdle is just trying to wrap our heads around the sheer scale of our planet and figuring out what's going on thousands of kilometers below us, totally out of our reach. Think about it like this. If I handed you some weird unknown fruit, what would you do? You'd just cut it open to see what's inside, right? Simple. But you can't do that with Earth. It's impossible. So to understand what's going on in there, scientists have to get creative and use models, piecing together all sorts of evidence to build a picture of the deep interior.
So let's take a quick trip based on those models. We'd start on the crust, this incredibly thin, fragile skin that we call home. Then, we'd plunge into the mantle, a massive layer where, as you go deeper, solid rock actually starts to flow, kind of like super thick, hot molasses. Deeper still, we hit the outer core, a churning ocean of liquid metal. And then, finally, right at the heart of our planet, we find the inner core. The temperature is insane, but the pressure from all those layers above is so intense it squeezed it into a solid ball of iron, harder than any steel we could make.
Now, here's where it gets really cool. This layered structure, it's not just sitting there. It creates this powerful, churning engine of change that shapes the entire world we see on the surface.
And this is all wrapped up in the theory of plate tectonics. This one idea was a total game changer, completely revolutionizing how we see our planet. The key takeaway is this. Earth's rigid outer shell, what geologists call the lithosphere, made of the crust and the very top of the mantle, it isn't one solid piece. It's actually broken up into these enormous plates that are constantly moving and shifting around the globe. And that movement, it drives everything.
So naturally, that leads to the next question. If these giant plates are always moving, what happens when they bump into each other?
Well, it turns out there are pretty much three main ways they can interact at their edges, or what we call boundaries. They can pull apart, they can smash right into each other, or they can just slide sideways past one another. And each of these interactions creates a completely different kind of landscape and tells a unique part of our planet's story.
First up, where plates are pulling apart. This is a diverging boundary. Here, molten rock from the mantle just wells up to fill the gap, creating brand new crust on the ocean floor. The Mid-Atlantic Ridge is the classic example of this, and the volcanic activity there is so intense that it literally created the entire country of Iceland.
Then you have the total opposite, converging boundaries, where plates crash together. And this is where the real drama happens. If a dense oceanic plate hits a lighter continental one, it gets shoved underneath, forming massive mountain ranges and volcanoes along the coast. But if two continental plates collide, well, they have nowhere to go but up, buckling and crushing together to form huge mountain ranges like the Himalayas.
And finally, at a transform boundary, you have plates that just grind past one another. But this is not a smooth process at all. The giant rock formations snag and get locked up, building up incredible amounts of stress over centuries. When that tension finally snaps, bam! All that energy is released as a powerful earthquake. The San Andreas Fault in California is probably the most famous, or infamous, example of this. Okay, so we have these massive forces constantly creating and destroying and shaping rock. Now let's get into how geologists can actually read the history that's locked inside those rocks.
The key to the whole thing is understanding what's called the rock cycle. Honestly, just think of it as Earth's ultimate recycling program. It shows how the three main types of rock are always being broken down, reformed, and transformed into each other over millions and millions of years. And when we say millions of years, we really mean it. Geologists had to create a special timescale just to handle this immense history. Just look at the Precambrian era alone. That one chunk of time covers a staggering 4 billion years. The timeframes we're dealing with here are just mind-boggling.
So how do we read this crazy long timeline in the rocks themselves? Well, one of the most important clues comes from sedimentary rocks, which form in layers, kind of like a stack of pancakes. We call these layers strata, and the principle is super simple but incredibly powerful. The layers on the bottom had to be put down first, which means they're the oldest. It lets geologists literally read history from the bottom up.
And every now and then, these layers hold something absolutely amazing: fossils. When an animal dies and gets buried quickly by sediment, its shape can get perfectly preserved as that sediment hardens into rock. These fossils are like incredible little snapshots of what life was like millions of years ago, trapped right there in the pages of Earth's stone book.
Okay, so let's bring this whole investigation from way back in the deep past and deep underground, right up to the surface, because this ancient story has a huge impact on the world we live in right now.
For a perfect example, look at the Precambrian Shield in Canada. This huge area is the ancient, exposed core of the North American continent, forged in a massive collision billions of years ago. We're talking about the oldest exposed rock on the entire planet, and because of its fiery, volcanic past, it's loaded with valuable minerals like copper, gold, and nickel that we still rely on today.
And the story doesn't stop with the rock. Over eons, wind and water break that rock down into the soil that's right under our feet. Soil is this complex mixture of rock bits, minerals, and organic stuff. And what's crucial is that its makeup, which comes directly from the rock it started as and the climate it's in, determines everything about what can grow there and how we can use that land.
You can see this play out perfectly in a place like Saskatchewan. In that one province, you get these totally distinct soil zones. The brown soils in the drier south, they support short grasses, but move north to the black, richer soils, and you can support entire forests. It's a direct line you can draw from the deep geology to the climate to the living world on top.
And it all comes back to time. The story we've just been reading didn't start thousands of years ago or even millions. We're talking billions. The rocks of that Precambrian Shield that give us so many resources, they are around 4 billion years old. That's the kind of timescale we're on when we read the story in the stone.
Which brings us to one last thought. The plates are still moving. Mountains are still rising. Erosion is still wearing them down. This whole geological story is being written right now, as we speak. So the question for us is, in this chapter of Earth's history, what clues are we leaving behind? What kind of record will future geologists find from our time?